Thank you, Eric, for the brief introduction. And before we start today, thank you very much for organizing this event here. I'm very happy to be here together with Paul Kilo, my colleague, and we're trying to give you a good overview about our software here in Riga today. And thanks for spending the day and the day with us and for your interest already at the beginning. Before we start, maybe a few slides about Dlubal software company. Basically, we are celebrating our 30th year of existence in the next year, and we are a company based in Germany with subsidiaries in Italy, France, Poland, and Czech Republic, and since last year also in the United States. Quite international company so far, and we're pretty much known throughout Europe, and with Germany as an exporting country. Also many other companies take the software in other countries, and that's why we have come up with a lot of codes and a lot of international languages, because our clients just demand that. We are known because of our software RSTOP and RFEM. There's often the question, what's the difference? When I have one, do I need the other? It's a little bit a historic topic for us, because when we started with the software, RSTOP was the main program, and we didn't have any finite element software that could handle surfaces, slabs, or solids. Over time, this came, and now we have both software, so you could call it the more simplified version dedicated to beam structures would be RSTOP, and RFEM is the more general structure that can handle also slabs, walls, solids, and of course also beam and column elements or frame elements. So if you want the full solution, you go for RFEM. If you can say, I only need it for frameworks, you could go for RSTOP. Both software have the more or less identical user interface, and the philosophy of working with the software is the same. So if you know one, you know the other one more or less as well. Yes, I've already mentioned that we are quite international company. You find all that information on our website. You can do design for steel, concrete, timber, but also we have individual solutions for membranes, glass, laminated CLT timber. Cross-laminated timber is a big topic right now. You may just go to our website and find all that information there, including links to social media where you can like the pages, and you will get informed continuously. There's a few logos from the companies that are our long-time users, and it's a growing field every year. So yes, I'm happy to be here today in Riga, because also the Baltic region here is a very interesting region for us, with a lot of new clients and a lot of new projects that we do here. On our website, you maybe also already know that there is a trial license you can download. For those who don't know the software, it runs for 30 days. You'll have access to our support team. Check it out, and if you have any questions, run into any problem, just let us know. Also, a good way to learn the software is to look at YouTube channels, where there's a lot of video material that you can look at. Okay, so far for the brief introduction to our software, and now to our company, and now I'm going into the software, and I'm going to show you. Maybe you will say it's a simple model, but I'm going to use it to show some basic things, some tricks, and some new things that we have introduced in the software, and I hope it will be interesting to all of you. what we're going to do now is to model something like this. We'll do a steel design, and we will compose a printout report, and I will point out a few specific things to our software. And then after that, I have several other models that we can go through. When we start with RFEM, what you see here, it's a 3D General Windows application. You can enter your project number or your project name. You can choose between a 2D or a 3D model. And you can also automatically create combinations according to different codes where you have access then to the combination factors. Everything here is set up for a variety of codes. If you don't find your code, the software is flexible enough that you can set it up yourself and you can change the factors because everything in the codes is subject to change. So we keep it more or less flexible. That all comes with RFEM Basic Edition. We can use a template. In this template, I have more or less saved like the materials or the type of units I want to have, maybe a set of printout report or views that I can use. A template is basically a model that you've prepared beforehand and you can save it as a template. Once I do this, a new workspace will open. The workspace is made from a 3D workspace here. We have tables in the bottom that are structured the same way like the navigation tree to the left. You can work in either part. Whatever you do in the tables will show up in the workspace or will show up in the navigation tree. So the grid is also customizable and you can set it up to like meter spacing or how many grid points you want. Now it's set up to 1 meter grid points and I can toggle between the different planes where I enter my model now. If I don't like to see something, I just can hide it. We work our way from top to bottom, and we start with materials. It's already set up as steel. The software comes with a material library that is also customizable, but it has not only metal, but all kinds of materials in there that you can imagine. And because there are so many, we also have favorites where you set up what you like to have in your model, so you can customize it. If you're looking for something, we have implemented a search function, so if you want to look for all the steels, you can just search here and you will find it quickly. Okay, I have already one set up. I'm going to enter now or show you how we can enter beams and columns. Basically, we can work from top to bottom or we can work from left to right here. I'm creating a new beam. I'm creating a new cross section. I'm going to the library of the cross sections, which are, again, many parametric ones where you can enter the dimensions or rolled sections that you can buy ready from the steel mills. I'm starting to do a column, wide flange beam with 220 size, made from steel, and I just fill out the dialogues and then I just can draw the columns like in a CAD application, and you see the coordinates running, and I just click in my beams, my columns. Okay, the same way I do the beams, I can do the columns, I can do the beams, and I use like a IPE 450 cross section again, and I can just go from here to here, from here to here. Okay, nothing really spectacular, but what you can do now is also you can select crossing the parts or catching them in a window like in AutoCAD, and then with the control key and left mouse key pressed down, you can just drag and drop and glue another frame on the existing part. Yeah? So it's very, very easy to work with. You can just drag and drop it and build your model in that way. It will automatically connect, and you can switch from a wireframe display to a full rendered view or a transparent view. So we'll use this throughout this presentation. Also, what is good or easy or often to use is you select the whole model and you use the copy move function that you find here. And we make a couple of copies in y direction, let's say 5 meters again in distance. And I have here some additional settings because I have a selected model now and I can create new beams or new members between the existing selected copy and the new ones that will be created. And I click OK, and you'll see here you can kind of extrude this model. The good thing now is if I do something wrong, I right away see it. I can quickly select it, delete it, and fix up my model as I want it to. When I do this, I have the option to do multi-selection, again with the crossing function. I can, when I have a selection, I can double-click on the members, and I can assign new properties to this member. Like I can say, oh, I want to have a different cross-section here. Let's say wide flange 160. Okay. And I also want to have a different type of member. Yeah? So there's beam, rigid member, ribs, truss only. Truss only means you can have, truss only end means you can have only axial forces. Truss means it is pinned on both ends and will also transfer bending moments. Yeah? So I save for myself to enter the hinges on both sides. Yeah? Okay, I'm doing this, and you'll see it gets a different thickness, that line, so I can see that there's something different. Okay. A good thing also is that you can, in the display navigator here, you can set up whatever you want to see. So I go here and say, for example, I want to see the cross-section outlines. So I can zoom in and see how the cross-sections are oriented. If I want to change it, again, the same concept, double-click, assign 90 degrees, and everything will change. Maybe here I don't want to have a pinned connection. I select it again, make it into a beam. And also I want to have a different cross-section. I create a new cross-section, IPE 360 maybe. Okay. Yeah, you see how we work with the software in a graphical way. With other software, you have to click on it, you have to find it in the navigation tree, you have to find the table and maybe edit something and do this multiple times. Here you can just select, or again, for example, add a hinge to a member end. I go here and say, okay, release condition in about Y and Z direction. You have also non-linear options here, plastic hinge, for example, that you can define. All things that are basic, standard RFEM features. Okay, so I apply the hinge here and you see a little hinge symbol. Good. Next, we'll assign a few supports. Again, select the support symbol. Hinged support is already set up. Okay, window over all the nodes, and we get the supports assigned. If I want to change something, selection, double click on the support, create a new support type. Let's say it should be fixed in all degrees of freedom. And we have here a fixed support. Okay. I need some bracing. Let's say here in this level, there should be some concrete or some slab or whatever, something that is like a horizontal stiffener. Yeah? So how to do this? You can go ahead and you can say, I'm introducing a nodal constraint. There's two types of constraint, equal condition constraint and diaphragm constraint. Diaphragm constraint means, okay, I have a diaphragm, stiff in the direction or in the level of the diaphragm, in the plane of the diaphragm, but flexible in vertical direction or perpendicular to the plane. So x, y, okay, I'm setting it up. I need to select the nodes or the plane. I click OK once again, and I have now a diaphragm set up. Huh? This is quite new feature. If I want to, it kind of irritates me to see that. So if I want to hide something, I go to the display navigator and say, please do not show nodal constraints. Huh? Okay. Next will be how to enter bracings. Yeah? There's a tool, you can say generate bracings in cells. Yeah? I have a toolbar here. Your tools can be also found here under tools, generate model members. Yeah? Bracing in cells, what does it do? I can set up a member type, tension only. I can say, please create a new cross section. If you know the naming, you can just enter it. That makes you faster. Huh? Then I can say, click icon, select cells here. And you see there is kind of cells that the software finds that you can just now click on, and it will create the bracing. Huh? So it's quite simple to do that. Okay, okay, and the bracing is there. Yeah? Maybe you want to change something. Nothing is so sure like a change in a structure while you're done. Yeah? Again, you can just select it, drag and drop it anywhere you like, move it to a different field. Yeah? As soon as it's the same coordinates, it will merge the nodes. Yeah? Also, maybe you want to copy it. Again, drag and drop it. Keep the control key pressed at the same time, and you can make a copy. Yeah? So very intuitive, very simple to work with this type of structures. I'm going to hide now my member cross-section outlines. Next, maybe I'm going to show you something else, a special feature that we have. It's called you find it here below in the tree under guide objects. It's a so-called line grid. It already was set up here. This line grid allows you to define grid lines and put their naming like A, B, C, 1, 2, 3, or small capital letters. You see a preview here. And I can set up now the dimensions so that it matches. Yeah? 5 meters. Yeah? Okay. And I have, of course, to show the line grids. Sorting here is the same way as in the input data. You have here guide objects, line grids, all. Yeah? And I can see here my dimensions. And if I want to also show the labels. I can also show the labels here. So now everything matches. The good thing about the line grid, and this is maybe something not everybody knows, if you check here, apply changes in model, and you change something here, let's say I'm going to change it to 4.5 meters, the C spacings, or the Y spacings to 5.5 meters, and I click OK, it automatically changes the model. So if I do undo, redo, so you kind of have a parameter that allows you to change the model. Maybe not always it will work in this way, but it can be very helpful. So remember this apply changes in model checkbox here. If you don't want to see the line grids, you just hide it again. Okay. Let's see what will be next. Next, we will start with some kind of loading. So we work ourselves down from top to bottom, and sometimes we come to load cases. So I apply a new load case. New load case. We have already set up Eurocode EN 9090 with some annex. And we can pick from some load case description here. Self-weight will be activated automatically. In the same way, I can set up several other load cases like snow, like wind in different directions, and also like live loads. For example, here. Automatically, you can pick the action category. That will help us then to do the automatic combinations. I click OK. The load cases are then visible here in this toolbox here. And also when I go back in the general data field, I can see here create combinations automatically. If I do this, it will then automatically also create load combinations. So when I go back to my load manager here, I can go now through actions, and I have 4 different actions. I have so-called combination expressions, which is like design situations. And I want to do now only ultimate limit design, so I can delete the rest. I have action combinations, so combinations based on the actions. And I have the resulting load combinations, in this case 21, and with automatically the load, the safety factors applied to it according to the actions. You get a nice overview. You will see exactly what the software does. Everything can be changed, including those factors, if you don't want to have the automatic combinations. At the end, we have a result combinations, which is an envelope of all the individual load combinations. So you get the max and min values in there. Okay, this is about the combinations. I'm going to show you one load case, how to enter loads. I'm going to do this with self-weight. You can do individual loading with linear loads, point loads, in all different directions. You can see here you have an explaining picture that explains how the load is acting, which is helpful because you don't have to have the manual, you don't have to guess what the software does. You have the units here, everything is clear from the very beginning. So you just enter a value and you can assign a load. Or what you can do is you can use a load generator, generate member loads from areas, loads via cells. And if I do this, I can say, for example, I want to have a live load of about 1 kilonewton per square meter on the on the, or 3 kilonewton on the roof. Yeah? So I pick the cells. Instead of the members, I pick the cells. Okay. I say, please do not load members that are parallel to a member. For example, I want the loads only on the frame beams. Okay. And I get this type of loading. Yeah? But I still don't know what is loaded. Yeah? If I want to see it, I have to right-click on it. Right mouse key is an important thing. Display separately, and you will see how the load actually is distributed. Yeah? I can do the same thing with the other level here. So this was the roof. If I want to know, it's 1 kilonewton per square meter. Okay. And I do the other thing here. And I say also maybe 3 kilonewton per square meter, but not on the top, but I want to, hang on, I want to have it here on these cells. No? Okay. You see what happens if you don't exclude the parallel members, it will distribute it in a triangular way. And if I click the parallel member, you will see it distributes it in one direction only. No? Important to know is this is one unit. If you want to change the live loading, you just click on it and everything will update. Yeah? Also, if you change the structure, yeah, everything will update because it's smart. Yeah? Okay. In this way, we can introduce also snow load, live load, wind load, and so on. In order to make this a little bit faster, I'm gonna save this model and then open a one that is already prepared for this. So we save some time here. Huh? So in this model, it's pretty much the same model. Maybe I did some changes because I did it live and a little bit different. But we have now snow loads, we have wind loads in 2 directions. Doesn't matter now exactly like what's the size of the wind loads. Just want you to understand that I have those loads in there. Yeah? And with all of this, I also have the combinations and I have my ultimate limit state combination. Yeah? Maybe a word to the calculation parameters. If I go to the load combinations, I have geometrical linear, second order, large deformation analysis, post-critical analysis. That all is part of RFEM. You have various options to change, modify stiffnesses, deactivate certain type of supports or members inside different load cases. Many different things. I'm not going to talk about everything now, but important linear, nonlinear analysis, including large deformation analysis. The software, the members are a 6 degree of freedom element in each node. So three displacements and 3 rotational degree of freedoms. It also can handle shear deformation. So if you have thick cross sections, it's also not a problem. Yeah? Okay, now I want to know what is my controlling load case, and then I want to do some design. To do this, I can do either a conventional design using buckling lengths, and it's always a kind of a typical critical thing to find out what's the buckling lengths and cumbersome to enter all of those things. Or I can do a second order analysis using imperfections. So for this, I want to know what is even the stability problem, the overall stability. So I'm gonna do a first analysis with my model here. You see, because we're doing second order, there are several iterations. And I'm trying to find what is my controlling load case. It's always important information what's controlling. Yeah? When I have the results, it's a result combinations. I get 2 lines with maximum and minimum. I can go through the other load cases and then show me what are the bending moments, what are the axial forces, and so on. I have set up my display, so it's a filled result diagram. If you don't want this, you can go here and you can say results, members, not filled. Yeah? Then you have the regular display. If you don't want to see this, you just, those buttons now are quite important here to check the numbers, to check the results on, off, and so on. Yeah? Okay, but still don't know what is the controlling one. I can do this by going into the first add-on module that I'm going to present, which is RF Steel EC3. And now I'm doing only a calculation of all these combinations for all members. And I'm going to do an analysis without stability, because I'm only going to do a stress analysis at this time. And I run the analysis. When I do this, I get for each load case, I get, for each combination, I get the controlling check. Also, I can go by design by cross-section, and I can say, please show me only the cross-sections that are the maximum results. Yeah? And I can see, okay, combination 12, combination 13, it's pretty often here for each cross-section. Yeah? If I want to see, for example, everything that is above, like, let's say 50%, I put here 0.5 and the filter. And then I see all the results that are higher than 50% in design ratio. So I can reduce this table here quite a bit. Yeah? When I see here, okay, combination 13, combination 12 is controlling. Okay? Good information. Combination 13, I go here, I can check the loading, it's wind in this direction, yeah? And so on. Yeah? Okay, why I'm doing this? Now I want to know for the one of the controlling combinations, I want to know the overall stability situation. And I'm using for this the RF stability module. I can select here, please show me 6 eigenvalues based on the initial forces of combination 13. So for one of the critical load combinations, I want to know the critical load factor, which is a good idea about the overall stability and also the mode, how things will fail when they fail. So first eigenvalue is 5.2, second one 5.6, 6.9. So that means I can increase, theoretically, the load 5.2 times before I get a numerical instability in second order. Yeah? How does it look? First mode, yeah? Let's see. I can go to the display and I can say something like this. Yeah? So first mode is like this. Second mode is like this. Yeah? Third mode is like this. So this is a good one because it's overall in one direction. Yeah? And the first mode is the most critical one that goes pretty much in the other direction. Yeah? So I'm going to use now this first mode and this third mode to create imperfection load cases. The second one is pretty much a local one here. This I'm going to take care of by doing a equivalent member method design in Eurocode later. Yeah? But I'm interested in the overall modes. Yeah? And I'm using this one because it has this way here in this direction and the other one. Yeah? Of course, there is a lot of things we can talk about here in defining the combinations, the imperfections. Okay, but how can I apply now an imperfection mode, which whenever it is, as an imperfection? I do this with RFEM. When I use RFEM, I can check a buckling mode. I can say the first case. I'm going to put it into combination 6. The first mode was not in X, it was in Y. Yeah. I have to change something first. I forgot. When I do this, as you see on the mode here, it's like a kind of buckles over several beams, yeah? Columns. So for this, I'm creating so-called set of members. How to do this? I can select here all my columns with the views here. Yeah? There's a generated view that is member by cross-section. I select all of them, and I make now basically one set of member. That means those two columns here are going to be one unit as a set of member. Right mouse click, member, generate member, create set of members, and with a few mouse clicks I created all of this set of members. Yeah? And I want to have my imperfection based on this set of members. Yeah? So now I'm going back to the imp module, open it, I say locase number 6, apply it to all set of members according to Eurocode 3. Yeah? Then it defines, it has a reference length, and it defines a pre-deformation or pre-camber according to plastic or elastic design. Now it's set up to plastic, and it has some kind of lengths or the member lengths divided by 300, 212, whatever. Pre-cambering ordinate. Yeah? If I do this, I generate this, and I look at my graphics, and I get an imperfection that looks just exactly like this imperfection I had. Yeah? Okay, I export it to load case 6, and I can do this with the other direction. Yeah? Now I have to do following. I maybe quick do it with the other direction. Hang on. I create a new, I copy the case. Yeah? Imperfection in X. Okay. It will be number 7. I say in X. I say imperfections for all, yeah? But this time I use the buckling mode number 3. Yeah? Generate graphics, so it's my other direction. Yeah? Actually it's in minus X, yeah? But let's not worry about it. Well, I can go back and I can set up, I can generate it, yes, okay. And then I can go to to change the orientation. It is easy because I can go to the load case and I can say, please apply a factor -1, and then it will change the direction. Yeah? So there's different ways how to handle such things. So now it goes in this way because the wind goes also in this way, so I want the imperfection in this way. Yeah? And the load case 6, hang on. Actually, I have to do the same thing because the wind goes also in this direction, so I can change this. Yeah? Okay, I go here, imperfection, calculation parameters, modify by factors, -1. Okay? So now I have imperfections, I have second order analysis, and now when I go to the Steel EC3 design module, I can set up my stability details, stability, and I don't have to worry about the effective lengths anymore, because in Eurocode it states if you have imperfection in second order analysis, you can use the member lengths as the buckling lengths. So I avoid all of this. Of course, if you want to, you can set it up, and you can set up for each member the buckling lengths, also using the results for RF stability, which also gives you the buckling lengths. Yeah? Okay, when I run the analysis now, and actually I have to do one more step now, because my combinations have now also imperfections. Let's take a look what happened there. Yeah? If I go here, I have imperfections, and I want these imperfections to be taken into account. Yeah? So consider imperfection load cases. I'm going to show you what happens. Yeah? So both of them will be combined automatically. And when I do this, we had now 21 combinations before, and now we have 42 combinations, because every combination can get an imperfection in this direction and that direction. The code also says you have to consider directions of imperfections into the most unfavorable way. Yeah? So I can do following. I can say it doesn't make sense to me that when the wind is going into Y, the imperfection has to go into X, or I want to predominantly have then imperfection in Y when I have wind in Y. So you have options to do this. Yeah? You can go here and you can say imperfection in plus Y should never be used with load wind in X. Yeah? And the same way in the other direction, load case 4. Yeah? So when I do this, then I have a different amount of combinations, and I get only 26 in this case. Yeah? So when there is no wind, it will use both directions. When there is wind, it will preferably use the one that is most unfavorable and most likely. Yeah? Of course, there's many things we can talk about here, but this is pretty much practice what I know from the user. Yeah? So, and with this, I have now 26 instead of 42 combinations, and I'm going to go and use those for the design. Yeah? When I do this, I'm going to have to add all of those here. I'm going to go into the stability design, and I run the analysis. Yeah? So we have second order analysis, imperfections, and a equivalent member design procedure according Eurocode, which should give me some kind of result now. Okay, now there is one problem because it's unstable in direction 20. If something like this happens, you can see here you get a hint. So it's something with this. Yeah? Calculation, to calculate. So now there is combination 10 and 22 is not running. So what's the problem? Okay, this way. Okay, maybe I did something wrong right now, or I chose a wrong member. Let me see. To check also the members, a good way is also to show here the colors in the rendering by the cross sections. Yeah? Views, visibility is off, rendering on, so you can see which cross sections are where. Yeah? Yeah. So I don't know what is the problem here. I think before I start now to look for all of these problems, I'm going to open the model that I have that has this already done. and we can look at this later. And now I'm going to open the model. Let me see which one I need to open. Okay, Baltic imperfections combo is this one. So with this, I have done the analysis in Steel EC3. I have all these combinations here, 26. I have my materials. I can rerun it basically then. Let's see what kind of cross sections we have. We have pretty much optimized cross sections here. Yeah? But now I want to maybe change something here because things are going to be different. For example, I want to have here a new cross beam in here. Yeah? How to do this? I can go ahead and also with the loading. Yeah? I can go ahead and introduce a new cross beam in here. I enter a new beam, new cross section, IPE 360, for example. Okay. It should be hinged. Yeah, so I put here a hinge on both sides. Okay. On one end here and on one here. Yeah, you see here the hinge. Same here and here. Yeah. Here I missed my center. I can just drag and drop it, yeah, and fix it. It's not divided yet. I'm going to use the same beam as here. So I select it, double click, pick a template member like this one. Okay, but I make some hinges on both ends. Okay, yeah. And then I want to connect it. I can use connect lines and members, and it will create two individual members from this here. Yeah? Okay. So now the model is connected. I can run the analysis. It should work. Yeah? Results are there. The only thing is my loading is not correct. Yeah? How to update it? I just edit the loads, and it tells me right away, hey, there is some change topology. Would you like to continue? I said yes. And then I will just fix the loading. Yeah? I'll just go here and say, please, I select the cells that are missing. Yeah? Okay. And also the parallel beams. Okay, the rest is the same, and my loading has been changed. Yeah? So this is quite let's say, automatic, because I have this load as one. Yeah? And I can do the same thing with the other loads here, and so on. Yeah? So it's quite easy to do. Actually, in some situations, you don't even have to do this. It automatically does it with the software. Yeah? But it's quite a simple way to update all those things. Yeah? And the rest, maybe one more time here, and then I'm done. I can do this. Yeah? Okay. I forgot to select the parallel beam. Okay, good. And now I can run the analysis again, and we do some optimization in the Steel EC3 module. Yeah? We go here and say, okay, materials are okay, cross sections. I introduced a new one, which is the one behind here. You see it's selected red. Yeah? Whenever you click on something, yeah, it will select it. Most likely we will not have the right results because it's too weak, the beams. IPE 180 is not strong enough, so I let it optimize. I run the analysis. I hopefully get now my results. And I get an optimization. And also, I have one more thing to show you then in the EC3 module. Now we have 94%, and you see here it made an IPE 330 out of it, and it made an IPE 300 out of it. Yeah? So this is something I can play back into RFEM, export all cross sections to RFEM, and I can update the results with the new weight, with the new results from these sections. Before we rerun the analysis, I have one more thing to show you. For example, here on the roof, there is let's say there's a steel deck, and I want to add here on this beam, I want to add here a rotational restraint. Yeah? I can rotational restraint, share panel, parameters, why can't I add it? Hang on. On this one, rotational restraint, materials, stress, okay. Run the analysis one more time. Yes. Let's wait. And I have to check if the analysis of the stability isn't there. Yeah, I need the stability check too. It was only stress so far. Yeah? And when I have this, then I can go to the rotational restraint, and I can pick here this cross section, enable the rotational restraint, because it will stiffen the rotation of the beam, top flange, for example, by a steel deck that I can select. I can select the steel deck from ThyssenKrupp, for example, 135, what is it, 75, for example, okay. And then I have to also define the type of connectivity, like where it is fastened, every pitch or every second one. Yeah? And then I also need to define the distance to the next beam, which is from here to here. Okay? And now I can run the analysis again, including the stability checks. Yeah. Now we have a little problem here because there is torsion. Torsion is a problem in the result, in the code of Eurocode, because stability with torsion is basically not allowed. What I can do here is I can check or I can optimize, and it will pick me a bigger member, but also the user has the chance to check out, okay, if there is torsion, now 5% of the limit shear stress is allowed. Yeah? I can set that up maybe to 10%. Yeah? It's up to the user, and I run the analysis again. And you see it is now okay. You can either change the model to avoid torsion, or you can say, okay, torsion, I know about it, but it's okay with me. Yeah? So we check here, that is 95, that is 1.73, and because the limit shear stress or the limit torsion portion is also depending on the cross section, I can also run an optimization and see what type of cross section will be possible to take that torsion. Yeah? So one bigger size will also take care of that. Yeah? Here, this one is not okay yet. We have to check that also. So let's optimize it. Okay. Okay. When I go to the graphics and I show my results in the graphic way, you can see here is the biggest. Here we have quite low utility ratios. Yeah? So maybe it's good to insert here a new cross-section. This type of section should be different. I double-click. I introduce a new cross-section. IPE again, maybe 200. Yeah. Okay. And we go to Steel EC3. Then we have to update this cross-section and run the analysis again. Yeah? So you understand how this iterative way of optimization works, introducing also the rotational restraint of the steel deck that increases the resistance to lateral torsional buckling. Then we finally get the optimized cross-section. Yeah? Because we have different internal forces, this may be a few circles. Now let's see what happened here. Maybe I can show you this. Okay, IPE 330, IPE 300. Yeah. Good. In order to get to the printout report and maybe to some other things I wanted to show you in this short demo, I'm opening the final model here now. That has everything ready. Basic structure. Okay. And with this final model, we're going to do some printout report. Yeah? Printing is also a very, very important feature. You need to get your results to a piece of paper. That's what you finally sell. When I do the printout report, I can work with so-called views in a good way. Yeah? For example, I can say here, this is my level. I create a new user-defined view. It's my level 1. Yeah? Okay. Yeah? So it shows up here in the visibilities. Yeah? If I'm going to cancel the visibility, I can say also another view is my frame here. Yeah? Okay. Maybe that's not what I wanted. Yeah, it's a combination now, level and frame. Yeah, works. Okay. The next view is maybe the roof here. Yeah. Okay. Or the next view is the members by cross sections. Yeah. This is a good view. Yeah. And I create a new visibility by this. Yeah. Columns. Okay. So now when I want to see something or I want to see some combined pictures, I can just click here and I have my views. Yeah? I want to have the roofs and the members. Yeah? For example, the roofs. I want this view to be printed in my printout report. So maybe I like to have the display without field diagram. Yeah? So I'm going to print this picture, and I'm going to use the printout report, window filling, and mass print. I'm going to use the height of 50% of the page. I'm going to select which results I want to have. I want to have all 6 internal forces of all combinations, maybe. Yeah? So I can select all. Okay. And I say, okay, please create my printout report. Okay. So now it will work in the background and build all those graphics for the printout report. Take some time. Here I can select also a template I have set up. Yeah. I'm using one that has a selection that makes sense for steel. And then a lot of those topics that I don't want to see are not used. Yeah. So it will create all these graphics. And I get here all my pictures from all combinations. Yeah. So I can navigate through here and it will give me all those pictures nicely arranged of all combinations. So you can do it in one workflow. Yeah? Many graphics. As soon as something changes, it will be updated. Yeah? Okay. Printout report is possible to be done also as a PDF. You have the option to file export as PDF. You will have a 3D, also a 3D PDF from one graphic. Maybe we should show this at the end. Yeah, and then I have one more other model I would quickly show you at the end. Okay, it's saving all those graphs. That takes some time. We have 95 pages. Currently, we're on page 27. So it's a quite reasonable amount for this type of structure. Yeah? Okay. If you want this picture here as a 3D PDF, maybe you want also this one. Maybe also have it in a display of cross sections or with diagrams or something like this. Yeah. You can print it to a 3D PDF and use this 3D PDF I'm going to print it to the desktop. You can print this 3D PDF and you can send it to anybody who has the PDF reader from Acrobat, and then you can also play with it, and you can rotate it, and you can look through there. There's many options in this PDF viewer. So it's a good communication tool. Okay. This is a quick run through this design with members in RFEM. You can do the same more or less in RStop, same way. Now, at the end, I'm going to show you two more things. First of all, I'm going to show a little bit about ShapeThin. ShapeThin is a new module that allows you to calculate section properties of any cross-section. Yeah. I have prepared a cross-section here that is actually a large cross-section. Dimensions are somewhat like 2 meters, yeah, because it's from a boiler house. Yeah. To show you how to work with this, I have one stiffener here, and you work basically the same way like with RFEM. You can drag and drop, copy the stiffeners if you want to. Maybe I want to do it here. Yeah. So you just copy it down to here. I have to zoom in a little bit because the snap points are so close together. Yeah. And then control and take it down to here. Yeah. Okay. Then you can analyze the cross-sectional values. You can see here the statical moments. You can see here also the section properties in the table, which is like the cross-sectional areas, the shear areas, moments of inertia, resistances, and so on. Plastic properties, everything is there as soon as you analyze those cross-sections. Once they are there, you can go ahead, save this section. It's called Baltic Boiler. And I can go to RFEM, open a new model. I'm going to give it a name. Okay. And when I open this model, I can use it inside RFEM as any other cross-section. Yeah? I can go here in the cross-section library, import from shape thin. And then here is my Baltic boiler cross-section. I have all the information about the cross-section like with any other shape in RFEM. Yeah? Okay. 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 And I can model this as a 10-meter column, for example. Yeah? I can apply here some kind of support. And I can apply some kind of load here. Yeah? For example, a nodal load of 600, 400, and 1,000. It's a big section, 1,000 kilonewton down here. Yeah? Now I can run it as an analysis, and I can do a stress analysis in the module, for example, steel EC3 or steel members. Yeah? I do the analysis, and I get the utilization ratio of about 42%. Yeah? Just like any other cross-section. Shear and equivalent stress. Yeah? Okay, but what about local buckling of this big section? What happens? Yeah? So just to show you a little bit what you can do also in RFEM. Control C, Control V. I make a copy in the distance of 10 meters. Actually, I wanted it to be here. Okay, now, if you want to check local buckling, you have to use a surface model. Yeah? How to do this? I can create a surface model, generate surfaces from member, just by a right mouse click and use this function here. Okay, and it will create surfaces from it. So within a few clicks, you have like a shell model of it. Yeah? What I need also is now I have this point support here, which I don't want. I delete this. I also delete this member and this line. And I need to make sure I have a support here now. To have a simple support, I can either put here a plate, or I can say I make a line support here, no? Like this. What you see here, those little symbols, are so-called mesh refinements that the software did automatically. I can go to the navigation tree and just delete them, because I'm going to set up my mesh directly and say, okay, 0.3 meter. Yeah? Okay. And now this load is kind of here somewhere in space. I need to make sure it's transferred to the column. A simple way to do it is to put here a rigid surface, a plate, that will then introduce this node into the column surfaces. And I can say the stiffness type is rigid, and make it from here to here. So this node is part of this rigid surface, and the forces will be distributed like within a rigid surface to the rest of the structure. And I can run the analysis now. Now I don't get bending moments like with the beam. Now I get surface results, like I get stresses, I get mx, I get my, I get axial forces, yeah, and I get also stresses here, like equivalent stress, membrane stress. Yeah? We have something like down here, something like 14, yeah, in this corner. Okay, but we were talking about local buckling, how to check that out. I'm going to use again the module stability, RF stability, where we can find, let's say, like 4 eigenvalues from this load case. Okay, and I get my critical load again. It's now 5.7, and you see what happens. It buckles down here. So if I want to have a stiffener, I have to put it down here. Yeah? And it's no wonder because my stiffeners are here and not here. So what can you do? The same way you work with members, you can also work with surfaces. And I can go ahead and I can say, okay, please let's look at this direction. Take these stiffeners here and we're gonna mirror them to the other side, create a copy in the XC direction. XC direction, let's see what happens. Yeah, almost what I wanted, but it's not a big deal. I just select it, isometric view, go here, drag and drop it, glue it on the other side, and if I do the stability check again, then the buckle will be probably somewhere else. Yeah? So now this other side is buckling. Yeah? But you see also it raised 7.9, so it's a good tool for you to find out where I have to do something, what is my critical distance from the stability case, and also it's a good way to show like how simply you can work with RFEM also in a surface model. Okay. I have a little bit more. I have one last example with solids, which can be done quickly. I've made this model just to show you also what you can do with RFEM. It's not only a framework program, it's also a general finite element software that is able to replace much more high overpriced software let's say, for structural engineers, because we have a lot of tools for structural engineers there with these load combinations, with this typical design for Eurocode and other international codes. And one thing what we use RFEM for is to do a in-deep connection simulation. Yeah? And I've done this little connection bolt and eye connection here for a tension rod with a solid model. So these are now all solids. Yeah? And what I'm going to show you is here, you can see it kind of delaminates from this bolt. So this bolt is in contact with this eye. So if I just show the eye and the bolt, you can see what happens here. It basically has only contact in the front because the loading, maybe I have to explain the loading, it's fixed here and the loading goes this direction. Yeah? So this is a new feature in RFEM. It's called surface releases. You find the feature in here, and this surface release, I'm going to delete it and run the analysis without it. When I do this, come on, because now this model is also a plastic model, so it has load increments. You will see that the bolt is connected to everything like one piece. Yeah? So now when I look at this here, it's like you cannot look through, it's deforming like it would be one piece. Yeah? Stress also, if I look at the stress, solid stress, you can see there's stress here, and we're about 2187. Yeah? So how to enter now this contact information? I'm gonna hide the results. This surface release is defined by selecting this, let's say, surface that is in contact with all the rest of the structure. I double click on it, and it's now a quadrangle and of type 0, but I select it, and then I go to the surface release and say, okay, new surface release. And then I have to pick it, it's this one, and I have to assign this type of surface release. The properties I have defined here is it's fixed in both directions, just a little spring constant, so it would not move out, so it's not kinematic. No? And then the UC, the perpendicular to the two plates, is also fixed, but it has a nonlinearity. Fixed if positive PC. No? There's two different or several different options, also with partial activity and diagram and so on. So the most often used one is like it acts in one direction but doesn't act in the other one, depending on the force. No? Okay, and now what does the software? It creates a second surface which is identical with the original surface, has the same position, but on the second surface I can attach the rest of the structure that should be not in contact anymore. Yeah, they can be off contact, and I can select basically this solid here, this one, and this one, and I have to select also this middle one, but there's two solids, so it's a little bit hard to select. I click OK first, OK. Results will be deleted, but there's another solid in the middle that I have to show you. This one, the center of the bolt, and it's solid number 4. And this one has to go there too, because it's also connected on the new copy. And I can just write it here, comma 4. Okay. So now the bolt and the eye are established with that contact condition, I say, and I can run the analysis again, and it will have this delaminating effect. Also, you can do things like slip. So if there's a little bit slip, then everything changes. You can look at all the results in deep. It's not a black box solution. Yeah. Let's see now the results of the eye and the bolt. And you see, before we had like red stripes here, now it's all over there. And also the deformation is then, it should be again as it used to be at the beginning. Yeah? So this is all possible with RFEM, with the same software. You do the Eurocode design, the same software you do the surfaces, stability design. You have the load combinations in there. We have all the engineering tools that we need in there. We can do the printout report and much more. And we also have concrete design, which will be in part of the next presentation. So with this, I think I have to finish. There will be much more to do. I hope it was a good overview about Dlubal software, steel design in general. And I think we're going to have a break now. Okay. And if there's any question, please approach me. I'm here. Thank you.